This one's had it right.
Not quite. Almost at the peak.
At the start of the week, that
All right. So, doing a little quick recap of what that video was. So there's this guy golfing, swings, aiming for that hole. We'll say he was way back here, the hole's over here. He goes way far right, lands almost in the people. So he goes over to that new spot, and now they have to figure out, okay, how far away is he from that hole? One of the announcers, one of the commentators says, oh, we can figure out he's X number of yards away from the hole by doing a little a squared plus b squared equals c squared. What is this guy talking about? A squared plus b squared equals c squared? Pythagorean Theorem, what? So a squared plus b squared equals c squared. This is what we're going to talk about today. What does that mean? So as far as I'm aware, that's just a bunch of letters.
A and B. It's a C. Square.
What am I squaring?
Array of variables. Like
Whatever those variables are. What do those variables represent, though? Like what?
the whole. That whole. So we're doing like a triangle.
Okay, if we're dealing with distances and triangles,
This is like
it's going to
finding
be
the missing
sides of triangles. Okay.
Is this like finding like a missing side thing?
So if we think about
The
it, we're looking
95
for
hold the ball and
the distance from the ball to the hole. So we're looking for a side. We're looking for a distance. We're looking for a side length, essentially, of a shape. So we can use this with triangles to find our distance from that ball to the hole. I'm going to the wrong spot. Okay, so it's going to relate to triangles. We've been talking about triangles. Just any triangle, though? Cube triangles, obtuse triangles.
I'm guessing you're
Guessing? Oh, you're guessing correct.
the 95 hole.
So the Pythagorean Theorem is something we talked about probably in 7th grade. It might have been the first time you learned about the Pythagorean Theorem. Would have used it in 8th grade. We used it last year in Algebra 1. So the Pythagorean Theorem only works for right triangles, though. So in order to find this distance, that ball to the hole, we need to create a right triangle, and then we can use the Pythagorean Theorem to solve for our missing side lengths. Because a squared plus b squared equals c squared is talking about your side lengths. But which of those side lengths is special? Or which of those letters is special? C. So we have to do something special with C. Which side length should C be? It's always going to be your longest side. And we call that longest side
The leg?
the hypotenuse. Good. Awesome, Gabe.
Yeah.
Did I say Gabe? I'm
it's
sorry.
like a
Triggered.
I'm sorry, Gage.
I didn't.
He's triggered.
So, but good. The longest side is always going to be your C of your hypotenuse. It's always going to be your C of your Pythagorean Theorem. It's your hypotenuse. It's our name we call it. So we need to create a right triangle for this situation to help us solve for that missing side. So we have a couple of distances here. We know from this sand pit to the hole is 136 feet. We have 95 feet to the hole, and then we have 36 feet to the hole. What was that? Actually, now that I think about it, I'm pretty sure the announcer does those yards. So you are right. I said the wrong unit. So it should be yards, actually.
Yeah, and you can notice the
I put it in yards. So how can we create a right triangle? What type of triangle do you see in these standing triangles?
How the 95 hole?
So the 95 to the hole. Like that one. So that does look very close to a right triangle, but this one's actually just a little bit larger. The way we could show it is if we had a bunch of graph and things like that and measure the angle, but it's just a little wide. But that's a good idea, good thought. Any other thoughts? So the 95, the hole is just a little bit larger than 90 degrees. It's like a 91 or 92 degrees. And we put it on a grid, you would be able to see it, but with this map it's still hard. Well, if we go to the 136, this does give us a right triangle. And my drawing doesn't really help us visualize that. But. And we know from this distance to the hole is 136 feet. Not feet, yards, I'm sorry. So, those two things up on the top? I think so. So we have 136 yards, and we have our missing side. But is that enough information to help us solve and help us use this Pythagorean theorem? What else would we need? Well, that's the distance we're looking for. We would solve for it, so we would like to know x, but we're going to probably have to do math for that one. What else would we need to know?
We know the ball to 136.
Yeah, we would need to know this distance here. One.
Oh, no.
Luckily, we had that. So we matched it where that's 91 degrees, or 91 yards, sorry. So we have this right triangle. We have 136. We have 91. Now, how would we use this information to help us solve for that x? So we had, sorry, let me just redraw a picture on this one. We had 91, we had 136, and we had x. How should we set this up? Say that one more time.
I thought that 136 was received.
Good. So our longest side of our triangle always needs to be our C. So we're actually going to have to take 136, and we're going to have to move that over and replace that with our C. That's good that we're putting in the information, but we just need to remember that's the biggest thing I think I see students mess up with the Pythagorean theorem, is they just forget that 136 or that C side always needs to be on that far side. They typically just want to put two sides in and then solve for C, but sometimes it's not always that way. Sometimes you're solving for the A, or sometimes you're solving for the B. So I'm going to call this x squared. So we put in that information to our a squared plus b squared equals c squared. Now, how would you go about solving this? What would you have to do?
Squared minus 91.
So we're going to have to square some information. So 136 squared, I believe, is 18,000 something. 136. Can't square. 18,496. And then 91 squared, I'll do it on calculator just to make sure it's right, is 8,281. And this is, we're going to have to leave x squared as x squared because it's a variable. We can't quite do anything with that quite yet. But we can solve for it. So how would you go about solving this? What would you have to do? We need to get x by itself, right? So how can we get x by itself? What should we get rid of? 8,281. So we can subtract that from both sides. Okay. So that gives us x squared left over because these cancel out. 18,496 minus 8,281 should be 10,215. So we have x squared equals 10,215. How are we going to get just x though? How do we get rid of the square? We need to do the square root. Inverse operation of a square is always going to be a square root. So our square and our square root cancel out. But if we do one inverse operation to one side, we have to do the other. So we'll have to take the square root of 10,215. And we plug this information in the calculator. Square root of 10,215 is going to be something like 101.069 something. So I'm going to round it to 0.07. And then we said we were talking about yards earlier. So we are 101.07 rounded to decimal places yards away. And so once again, we can use Pythagorean theorem to solve for any side of a missing triangle. As long as we have a right triangle and as long as we have two sides and we know how to set it up, we can solve for any of those missing sides. And it's going to work every time for any right triangle, which is awesome and a good skill to have in a good theorem because we get right triangles a lot. And actually, if you were to listen through that video again, but there's a part where like the audio cuts out when he says the distance, and if you actually listen to it, he says, "Oh, the best way we can figure out this is 101 yards by doing a squared plus b squared equals c squared." And so we had it right. So good job, guys. I need to pass out the paper. So you're getting 2 pieces of paper because I forgot to hit the staple button on it. Okay, so my bad.
There's a staple for you?
You think I have to go through and staple all these papers I've handed you in the past by myself?
Yeah. So
No, the copy machine has a staple on it.
it's like print.
All right.
But yet we still have one more for broadcast.
Yeah.
So let's snatch my stuff.
So, Pythagorean theorem. Before we jump into using Pythagorean theorem and talking about it a little bit more and some shortcuts with it, we're going to talk about why it works, or like really how it works. And so what the Pythagorean theorem really says is, instead of just saying a squared plus b squared equals c squared, just saying some random numbers, what the Pythagorean theorem really means is if you have a triangle with some side lengths, it's really bad highlighting of my triangle. You have a triangle, and you take those two shorter side lengths. So we have a shorter side length of 3, and a shorter side length of 4, and our longer side length of 5. If you take those lengths and you create an area with them, square them, 1 times width, create a square, the area of both those squares will be equal to the area of your longer side square. So 3 squared is 9, 4 squared is 16, 5 squared is 25. So 3 squared plus 4 squared equals, what's my pen do? It's not fun. 3 squared plus 4 squared equals 5 squared. What's happened? So 3 squared is 9, 4 squared is 16, 5 squared is 25, 9 plus 16 is 25. So really what it's saying is, if you create the area from those side lengths, if you square those and create a square area, those areas will always be equal to each other, or the largest area will always be equal to the smaller two added together, for any right triangle. It doesn't matter what side lengths are for anything. And later on in the year, we'll actually prove this for any triangle rather than just showing an example. We'll actually sit down and do some algebra and prove it, but we won't worry about that at the moment. We'll worry about that towards the end of the year. So the Pythagorean theorem can be very helpful for solving for any missing side. And we practice that. We've done that in 8th grade, 7th grade, 9th grade. We've used it for solving for missing sides. But it can sometimes be a little bit tedious of setting it up and solving for it and taking the square root and squaring this and squaring that and minusing this and minusing that. And so there are a couple of shortcuts we have to Pythagorean theorem. We call these Pythagorean triples. So what a Pythagorean triple is, it's a set of 3 side lengths that are always going to be whole numbers. And so there's certain triangles, and there's certain side lengths of triangles that when given these specific 3 numbers, you will always have whole numbers. So like on that first example we saw, we had the 136, we had the 91, and then we had the 101.079, whatever, repeating. And so that using those repeating numbers, that's not always fun. Using those irrational numbers, we don't like it. We like to have those integer whole numbers. So Pythagorean triples are sets of Pythagorean, or sets of right triangles that will always have whole numbers. And they always have these specific triple digits. So a 3, 4, 5, any triangle with 3 and 4 will always have 5 as its last side length. Any triangle with 5 and 12 will always have 13 as its last side length. Any triangle with 8, 15, 17, or 8, 15 will always have 17 as its longest side. So these are specific triples that if we know 2 of the side lengths, you automatically can always know the answer to the third one. It takes a little bit of memorization. It takes a little bit of time to be able to recognize these. But rather than having to do the Pythagorean theorem for all of these numbers and find them out, if you can recognize a Pythagorean triple, you can solve your answer just automatically just by knowing it's going to be 6. Because it doesn't work for not every triangle has a Pythagorean triple. Like that first one, the 136 to 91, the 101 point something like that. That 101 isn't a rational number. It's not an integer, and so it doesn't work for a Pythagorean triple. But Pythagorean triples show up a lot, and typically math teachers and typically math tests, when they don't want your answer to be an integer, or when they don't want your answer to be an irrational number, they're going to give you a Pythagorean triple. So if you can recognize those Pythagorean triples, you can typically solve the problem without having to do any math. Which can be nice. The Pythagorean theorem isn't bad though. So the Pythagorean theorem works for any triangle, and you can always use the Pythagorean theorem to check your answer, or always use the Pythagorean theorem to find the answer. But this is just a shortcut. It's just a nice, easy one. A cool thing about the Pythagorean triples as well, if we think about dilation, one of our transformations, we think about similar triangles. They're always multiplied by a scale factor. They have those proportional sides. So if you multiply one side by 2, all the sides of that triangle got multiplied by 2. Same thing works for our triples. If I have a 3, 4, 5, if I multiply each of those side lengths by 2, 6, 8, 10, that's also a Pythagorean triple. I can multiply them all by 3. That would be 9, 12, 15. That's also a Pythagorean triple. So these Pythagorean triples also work for their multiples. So if you notice a multiple of the original Pythagorean triple, that will also work as a triple. So the main two that show up, and the main two that I have memorized, are 3, 4, 5, 5, 12, 13. The other ones don't come up as often, but if you can memorize these two, these ones come up pretty frequently when solving problems. And so those are just nice numbers to know. So the way these work, though, is if you see a triangle and you see a missing answer, you can automatically know what that missing answer is as long as it relates to a Pythagorean triple. So 5 and 12, I know my missing number has to be 13, so my longest side is 13. 16 and 34, I know 16 is 2 times 8. I know 34 is 2 times 17. 8, 15, 17 is a Pythagorean triple. So 2 times 15 will give me 30. And so if you can recognize these triples, you can solve these numbers very quickly and find these answers very quickly, rather than having to do 16 squared plus b squared equals 34 squared, and square 16, square 34, subtract 16 squared over. And what was that? No, so these are things you'll have to memorize. So I've worked with math for a long time, so I have 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25 memorized. But if you can, it takes a little bit of time to be able to recognize it. So it takes a little practice, takes a little use. So if you don't recognize these right away, use the Pythagorean theorem. But these are just things that you can use some shortcuts to have that can help save time, help save problems. So see if you can take a moment, see if you can find the other two numbers of this Pythagorean, or the other two missing sides of these Pythagorean triples. So look through those numbers, see if there's multiples of one of your Pythagorean triples, and see if you can figure out what that missing number should be. If you can't figure it out, use a Pythagorean theorem anyways, and use that to solve. Okay, so what did we find for those missing sides of our right triangles? I had 9 and 12 for one of them. What's my last one? 15. How do you come up with 15?
3 times 4 is 12, and 3 times 3 is 9.
So 3 times 4 is 12. 3 times 3 is 9. If we think about our triples, we have a 3, 4, 5 triple. So 3 times 5 is 15. Good. What about for our second triangle? Okay, what do you find for this one? 96. How do you come up with that? What was that? How do you know it was 24? What are the other two?
7 times 4 is 28. 25 times 4 is 28.
So you know 7 times 4 is 28, and then 25 times 4 is 100, and one of our triples is 7, 24, 25. So we can do 24 times 4, and that gives us 96. Good. So once again, Pythagorean triples are great, and they're good shortcuts, but they're not the only method. Using the Pythagorean theorem, the traditional method, works every time, as long as it's a right triangle, so that's always the way you can go about it. You don't have to use the Pythagorean triples. And they won't work for everything, it's just sometimes they have shortcuts. So with Pythagorean theorem, we're often taking square roots. So when we deal with square roots, we often deal with irrational numbers. We're going to get those weird, ugly numbers like that example we had earlier, the 101.07 on and on and on and on number. So with Pythagorean theorem, when we deal with square roots, oftentimes we want to leave these numbers in exact answers. So we don't want to have to round. And so with exact answers with square roots, we call those simplifying the radical. And this is something we talked about last year when we dealt with the quadratic formula in Algebra 1. When we have the quadratic formula, we have to simplify those radicals into into smaller numbers and get numbers outside the radical. So we're going to do a quick review on how to simplify radicals, just sort of to catch us up and help us solve these when we might run into them with the Pythagorean theorem. So in simplifying radicals, we have to think of two numbers that were multiples of your numbers on the inside. So 14 and 2? Okay, good. So 28 is multiples of 14 and 2. Now when we start these factor trees and break them up, we have to break them up as far as we can into those prime factorizations. So we can split it 7 up into 2, or 14 up into 2 and 7. And now 2 can't be broken up any farther, 7 can't be broken up any farther. Those are prime numbers. And so we circle them and cross one out. So you circle any pair you have, so we have a pair of 2's, and then one of those 2's gets canceled out. The other one has to go on the outside of my square root. So 2 is going to go on the outside of my square root. And then any number that didn't have a pair is left on the inside. So 7 is my number that doesn't have a pair. It's left inside my square root. And so 2 radical 7 is the square root of radical 28. So we can do the same thing with 162. What are some numbers I'm multiplying at 162? 81 and 2. And if you're having trouble thinking of some multiples, one strategy to look is, okay, this is a multiple of, it's an even number, so it's going to be a multiple of 2. So I can just divide my number by 2, and I know 2 and 81 would be possible. Can I think of any multiples of 89, or sorry, not 89, 81?
9 and
9 and 9. Can I think of any multiples of 9? Now 3 can't be split up any farther, so I need to circle my pairs and see what I have left. Cross one out each. So that gives me 3 times the radical of what's left over, which is just 2. So 3 times 3 equals 9 radical 2. And that's my solution, or my simplified radical.
So you're multiplying your leftover.
Because if we think about it, when we're doing these factor trees, we're always thinking of multiples. What are 2 numbers that multiply? So when we get down to our answer, we're thinking of 2 numbers, or these 2 numbers are going to have to be multiplied by each other at the end. Same with any numbers left over on the inside, they're all multiplied by each other on the inside. One thing you could have also recognized is we had 2 9s here. We could have circled these pairs of 9s and canceled one out and put it on the outside. We didn't have to break it up any farther. As soon as you get 2 pairs, you can stop there as well. So that's another strategy. Now, sometimes, this won't happen as often with Pythagorean theorem, but sometimes we get numbers left on the outside before we get started. What do we do when we simplify and there's a number on the outside? So when we get to our answer at the very end, we'll bring that 6 back and we'll multiply it at the end. Like how we multiply these numbers at the end, we'll bring the 6 back. But right now, we really don't have to worry about it at all. We just need to worry about the 32. So what are 2 numbers that multiply with 32? 8 and 4. Okay. Can I split this up? 2 and 4. Now we can split 4 up into 2 and 2 and keep going with that. Or I can recognize, oh, I have a pair of 4. I can just circle that right now. And that leaves me with just 2. So I have 4 on the outside and then 2 on the inside. But I had that 6 at the very beginning. So once again, I need to make sure I need to bring that 6 down. I can't forget about it. And so 6 is also going to go on the inside. So 6 times 4 is 24. So 24 radical 2 is our solution. Our simplified radical. So now when we're dealing with Pythagorean theorem, when we're dealing with radicals, and when we have these numbers, we want to make sure our answer is as accurate as possible. We don't want to simplify. We don't want to round early. So unless it says otherwise, unless it tells you to round to the nearest hundredth place or something like that, leave your answer in a simplified radical form. Leave your answer as simplified as a radical as possible. Sometimes that you might get a radical of a prime number. Sometimes it might not be simplified any farther. It might just be that answer. Or sometimes you might have to do something like this, but we want to try to keep it as accurate as possible. So we're not going to round early in these cases. On the state test, unless it says otherwise, you can probably round, but they might say keep answer in simplified radical form. So it really depends on the question they're asking and how they ask the question, but sometimes they might have you round, sometimes they might have you not, or sometimes they might take either answer. But just to be safe, we want to know in both ways. So we're going to see an example of this. So we have a triangle here, and we need to find the length of that missing side length. So if we think about, it's a right triangle. I'm looking for my missing side length. I can use Pythagorean Theorem, a squared plus b squared equals c squared. C squared is always my longest side, so that's the side I'm currently missing. So I know it's going to be 6 squared plus 5 squared equals my x squared. I can leave that c squared, it doesn't really matter what variable it is. 6 squared is 36. 5 squared is 21, or not 21, 25. And then that leaves me with x squared. I'm going to have to add 36 plus 25. Should give me 61. This equals x squared. Now, in order to find x, I need to take the square root. I need to get rid of that square. So I'm going to square root both sides. Cancel my square out. And that leaves me with x is equal to square root of 61. I have to figure out what that is. Now let's think. Are there any factors of 61?
No.
Right. Now, 61 is a prime number, so we actually can't factor it any farther. It's already simplified as much as it can be. So we're just going to leave our answer as square root of 61. And that would be your solution. So rather than having to simplify farther, or rather than having to do the square root of 61 and get a decimal, we're just going to leave it at square root of 61. If it was something like 62 or something that did have a factor to it, we would simplify farther, but with this case, it's just a number. And I think we'll do this last example and we'll stop there. So we have two side lengths, 4 and radical 65. Which side is my longest side of my triangle? Radical 65, that's my hypotenuse. So I'm going to be solving for either my A or my B, it doesn't matter which one. So if I set this up, it's going to be 4 squared plus x squared equals radical 65 squared. Now 4 squared, that's easy, 16. 16 plus x squared. What is radical 65 squared though? What's a square root squared? So they're not the same thing, they're actually opposite things, right? And so a square root, what? So a square root and a square are opposites. So if we're taking the square of a square root, that's just like taking the square root of a square, it's going to cancel itself out. So our square and our square root are going to cancel out, and we're just left with what's on the inside, which is just... Oh, okay, I'm sorry.
Yeah.
I thought you just meant it was going to be the square root of 65. I'm sorry. Or I thought you meant a square root and a square root of 16. I'm sorry.
Okay.
Good job on that, though. Sorry about that. But yeah, 65. So square root and square root can cancel each other out. So if we square root, same thing is just like square rooting a square. Cancel itself out. So we're just left with the inside. Where would you go from here? How would you solve this? Okay, x on its own. So we need to get rid of that 16. I'm going to subtract it. It's a positive number. And we have x squared equals 65 minus 16. Put that in the calculator, that gives us a little bit of 49. Last step, we need to get rid of that square, so we're going to square root. Use those inverse operations again. And then leave us with x equaling square root of 49. 7. This one also, you don't have to simplify any farther. It's just going to leave us with an integer answer. And so we solve x equals. Any questions about Pythagorean theorem for today? we're going to continue to practice this a little bit more tomorrow. And starting Wednesday, we're going to talk about something called special right triangles, which these are things we will have to memorize, and you'll have to learn a little bit about. But special right triangles are a very helpful tool with solving for missing information as long as you know what they are.